All I have to do is find my paper. Anyway, welcome back, everybody. This is William M. Briggs. We're on episode 23 of Uncertainty and Probability Theory, the Logic of Science. Today, infinite hypotheses. This is a direct continuation of last week's lecture, number 22, where we talked about going to the continuum, where our new hypotheses kind of live, but only as an approximation. I stressed over and over again, only as an approximation to the finite discrete universe in which we can take measurements. Now, this particular class will be almost all math. So if you don't like math, you can switch off now and read the written lecture instead if you don't want to listen to the whole lecture. We have to get through this math. It's not that difficult. I don't think it's that difficult. It's just elementary calculus, nothing more than that. But we need to understand what we're doing with this math. The probability, as I said before, can be wonderfully mathematical. You could go off into town and prove theorem after theorem, write all these thick books on probability math and so forth. There's nothing wrong with that. It's perfectly fine. You could do this with mathematics too. You can prove theorem after theorem after theorem and just go to town. None of that becomes a problem until you want to apply that math to propositions in which are measurable or are useful or we're going to do something with. When you start applying the math to real life, why then we have to have a philosophy. It's inescapable that we have to have some kind of a philosophy. So we're going to do this math, but we're going to interpret it philosophically. Now Jaynes does this same thing. This is 4.6 and 4.7, 4.8, the last part of chapter 4 in his book. So that'll be the homework, really, read all this kind of a thing. Now you remember the last setup we had some machine that's going to be putting out some proportion of bad widgets, whatever that's going to be. It's going to be putting out, and it's going to be finite. No matter how long this machine lives, it will live a finite amount of time and put out a finite number of widgets, even if that number happens to be very large. But because it's easy for us, and it does provide very useful, nice results, we're going to jump to the continuum and use approximations that we develop just to make our life a little bit easier, in which there's no problem in doing so, as long as we always keep in mind that's exactly what we're doing. And I'm going to emphasize that many times. So let's remind ourselves we're interested in the proposition of interest A, which is the proportion of bad widgets that are coming out of this machine. Let me just write it up. We'll just write up Bayes' theorem here again, and we'll talk about these pieces. Okay, A is our high proposition of interest. The proportion of bad widgets is F. That's what we're going to have in a second. D is whatever data that we observe from this. X is whatever information we're bringing to the problem. Namely, the proposition that we have a machine that's going to be spitting out a certain proportion of bad widgets. And we're going to take some observations, data here, D, in which, so let's just write up all this right here. So we could say A could be, we're going to be very explicit about this. A is going to be the fraction of bad widgets, which are going to live in the interval F to F plus df. This is our proposition of interest. And D is going to be, we observed, is it n and n minus 1? Whichever we have. Yes, n bad. It doesn't make any difference. And then n minus n good. We've taken some observation. These are our propositions. X is, I'm not going to write it up, but that's everything I've said so far. We know that we have a machine that's going to be spitting out a fraction of bad widgets, and we don't know what that fraction is, and we're going to test various hypotheses. And remember, we're not trying to do anything. By testing a hypothesis in our language, all we're doing is giving probabilities to the hypotheses that we have of interest. What you do with that probability is something entirely different. It is not directly related to probability. That's a decision. Whereas in classical hypothesis testing in the frequentist and Bayesian sense, they're trying to make a decision for you. We're not making a decision. We're just giving you the probabilities. All right, so that gives us that the probability of A given x is going to be, we did this last week, is going to be some discrete, or rather continuum based probability like this. This is, everything is discrete here and finite still. We have this density. If you remember last week, we derived this density by doing the mathematics that gave us, we increased the interval of the number of bad widgets that we might have, and we increased the fraction of them. We let that go to the continuum as an approximation, and we took the derivative of that thing, and we have this density. This together, though, is still a discrete finite thing until we let this go to zero itself, df go to zero itself. But this here is the probability. This is the probability of this, the fraction bad, and this interval is this particular beast right there. Now, unfortunately, I have to erase the board. Well, I don't have to erase it. I could say, you can see over here, that's because this is going to be the probability of A. Then this right here, this probability of after we observed our data will just be g of f given dx df. If we let this stand in for A right here. That's all it's going to be. It's going to be its own probability after we observe the data. So there's no problem with that. Now, the interesting thing about this, we talked about this denominator here before. It's not necessarily or strictly needed. Now, I do have to erase some board space here. We can calculate each of these things, and we can get the exact numbers. But we realize that this particular thing here, this has to be a probability. A probability we've already proved back episode 4 or 5 or 6, I can't remember which, has to be a number, and it lives on 0 and 1. So this has to live on 0 and 1. So we know we could get away with saying the probability that f is some fraction in 0 to 1 is simply going to be this particular beast over here of g of f dx df equals 1. So we don't have to actually calculate this piece right here. So perhaps I'm going too fast. The idea is, if we didn't calculate this denominator right here, we'd only have this particular thing, which is g of f x df. We have our data model, I guess you could say, because if x specifies how we're figuring all this kind of a thing out. We don't necessarily have to calculate this, because this thing right here has to have the property that it integrates over the entire range of possibilities into 1. So we could just find the constant. We could calculate this times this, and then at the end we could calculate this, which will give us the constant to multiply this, so that we get the probability that we want at the end. It's just a little bit of a numerical trick. You don't have to. You're certainly welcome to calculate all three of these things and to get the exact probability that we want here. Okay. Now, here comes the philosophy. Here comes the philosophical part of this thing right here. It's okay, we're going to do it, and it's pretty obvious what's going to happen as df goes to 0. We can let this go to 0, and we're going to have no problem developing an approximations to it. But a lot of times these problems have parameters besides just the f. We're going to have this particular thing right here, and these priors here may have themselves what are called hyperparameters. They may be parameterized probability distributions themselves. So suppose df equals some epsilon by h theta, for instance. Now we can let epsilon go to 0, and then therefore df will go to 0, and epsilon times hf times h of theta will go to 0, no problem. But it could go to 0 in a lot of different ways depending on every possible value of theta in this particular function. In other words, this beast, I'll call it, maybe I'll give it a little wavy line over it like this, as opposed to just this one up here. We can let this particular thing go to 0 when we have no other hyperparameters to worry about. And it's going to give us the right answer, and I'm going to prove it to you in the same way Jaynes does. It'll give us an answer that's perfectly consistent, no problem. We're not going to run into any difficulties interpreting it. But if we allow that this thing has a parameter, that one of the prior or the data model has these hyperparameters in them, we could let epsilon go to 0, but it could go to 0 in a lot of different ways. Each of these different ways can produce a different answer at the end. And in fact, that happens, and it happens all the time, and it generates a lot of different probability paradoxes, one of which is the Borel-Kolmogorov paradox. Now, we're going to get to that in chapter 15. I'm not going to tell you what it is now. We're going to get to it when we get to it. But I told you many times, infinity is a very big place, and it really depends on the direction that you take to get there. All right? It depends crucially on the path you take to get there to get a different answer. This is a very straight path. This is a crooked path, in fact, infinitely various, that could give us different answers. So we got to be very, very careful about all this stuff. This is the first bit of philosophy. We're doing this approximation here already. We know we're doing an approximation because reality, our measurement of this device can't be infinitely gradated or take infinite gradations. However, as a useful approximation, we might let it. This type of model here we'll come to eventually too. In fact, these are the most common types of models right here. All right, so now let me erase this part here. We'll keep up our model here. So let's just show you that we could get away with taking this df to 0, and it's going to give us the right answer. And it's not going to tell you anything that you don't already sort of see if you're mathematically inclined and so forth. But we're going to pay very close attention to this result because we want to understand precisely what's going on every single time we do a calculation that we're going to apply to real life, which we're going to apply to our real life widget machine right here. So we really want to understand precisely what's going on. So let's bust up A into a separate. A, remember, was the hypothesis that was between f, the fraction, and f plus df. But so let's break f up into pieces, and then a2 to an be in the interval. This a1 will be some exact hypothesis that is equal to f, and the rest of these will be in the interval, the f plus df. This is exactly f, and this is the interval f plus df. So we have a1 equaling f. We're going to call that our hypothesis about f, and we have all of these others, however many there might be, in this interval f plus df. Okay? Now, if we look at this, we're going to have the case that the probability of the data, this is the Boolean, we're going to use the Boolean notation a1 plus a2 plus an, we have x, and that's going to equal the Boolean notation a1 plus a2 plus an. This is we have all of these different hypotheses now, and I should just write it out like this. I should say a equals a1 plus a2 an. a1 is mutually exclusive to all of these, and these are exclusive to all of these, so we're going to write this Boolean algebra like this, and that's going to be very simple. The probability of this particular hypothesis right here now, when we're breaking A out, is going to be, if you could see this, it's going to be this particular thing, the probability of each AI given x times the probability of the data given this A, x, I, divided by the probability of AI given x. Okay, what have I done with this? I hope I'm not confusing you too much. I'm just writing all this out. We're writing this Bayes formula again when we break A up into little pieces. We're going to let for the first A equal F, and we're going to let however many there might be other A's that are going to be chopped up into this interval right here. Now, because they're going to be in this little tiny interval, we'll first suppose that each one of them are going to be equal. In other words, we're going to suppose that each A2, A3, A4, A5, all the way up to AN are equal and different than A1. Just suppose that for the first second or two. And that's going to give us, well, I won't write that up. I'll just say it in words. I'm going to suppose all of these are equal. So in other words, I have to write it up. The probability of AI given X is going to be the probability of D given AJ given X where I and J don't equal to 1. This is supposed to be a J. We're just going to say all of these are going to be the same. And if that's the case, now you can kind of see what's going to happen. These things will all factor out. The priors won't make any difference. They'll go away. And we'll be only left with the probability of the data given HFX equals this. That's if all of these other hypotheses where all the A's are equal. Now, if we let this right here, we let these number of A's go to, we let the DF go to 0 in this particular interval now, that's the same thing as n going to 1. So we have proved that this whole thing, if we split this interval up here, into F itself, or any number of discrete possibilities, and we assume that they're all, we don't even have to assume that they're all equal. As long as we let this DF actually go to 0, the number of these has to go to n to 1. The number of possible A's that we can stick in this interval has to go to n to 1. And therefore, we're left with this hypothesis that it's going to just be F. The probability of the data is going to be whatever the value of F is and X. That's a long-winded proof. And the point of all that kind of thing is, is just to show you that we could absolutely do this and staying in a very simple above-board way where we've taken care of every possible route that we can get to infinity. That's the important thing. And we come to the same answer every time. All right, so that's that first part. And the point of all that is there's no hyperparameterized distributions of the data or anything like this. So we've proved using our basic rules of just basic rules that we deduced about probabilities, we proved that all works, Bayes' theorem works, and as long as we just use very simple mathematics, may not seem simple to you, but it is simple as far as you can go in mathematics, that we come to the right answer. We won't get goofy answers or anything like this. So suppose the probability, we're going to have the same hypothesis here. Suppose it's going to be the case that the fraction of correct, the fraction of bad widgets is in fact F, some F. And so we're going to observe n bad ones and capital N minus n out of however many they're going to be good ones. And so we could just deduce that that's going to be, if we know that F is the right answer, the probability distribution for that, for seeing any particular value, is just going to be the binomial theorem. Because we know, we've already deduced the binomial a long time ago, and we're saying we know what F is, and we're saying we have so many F's, and the order doesn't make any difference. We know we're going to have n total widgets put out by the machine in our sample that we're taking of D, and n of which are going to be bad, little n are going to be bad, and we know F is the true fraction of bad ones, and so this binomial theorem holds. So that means we could write this up. This is what Bayes did. This is what Thomas Bayes did right here. This is the sort of historical bit. So we could write the density. I'll get out of the way so you can just see. We could write this density of f after we've seen the data, the so-called posterior, is going to equal this. We know it's going to equal this because if this is the true, it has to be this, multiplied by the so-called prior distribution, and divided by that the data distribution itself, integrated out, which is going to be this. I'll just write it up and I'll explain what happens. Fn 1 minus f n minus m gf x df. This appears in both the numerator and denominator, so it drops out. This is just a normalizing constant. This is going to be integrated with respect to f, so it'll just give us some sort of a constant out of this, and that constant turns out to be, if my memory is right, is n plus 1 factorial divided by n factorial, it should be n minus n. It is n minus n factorial. So that's what this equals. This equals this beast right here times this. And that becomes, and you can look this up in the books, a beta distribution, or a beta function, I should say. So that becomes a beta distribution. That gives us the probability density over all possible values of f. Now, we could take this same function right here, We've calculated what it is if we assume that f is the correct proportion. And we have this formula here. We integrate out this stuff here. We integrate out f, so we get our constant, which is this. And all I want you to remember is the binomial part of this. And so what we're going to do, here comes the little trick. We haven't done anything so far, really. But here's the trick, the kind of a fun trick. We're going to define LF to be the log of our density here, our so-called posterior density. All right. And if you remember what we did, we're going to take n log f plus n minus n log 1 minus f plus some constant we don't care about. Just taking the log of that particular function. If you don't remember, you can go pause back at the thing. Remember, it was f to the n times 1 minus n to the n minus f times that constant, which was n plus 1 factorial over n minus n factorial times n factorial. And all we're doing is taking the log of that, no problem. So let's let f, with a hat on it, equal n divided by n, which is the fraction of the observed fraction of observed bad ones. We've taken n total, we have f over n. We have n over little n over big N. That's just the fraction, the relative frequency, if you like. The relative frequency of these things. Okay, so now what we'll do is we'll do a Taylor series around this LF right here, just for a couple of terms. And we'll center it around f prime. So LF is going to equal, in a Taylor series expansion, L of f hat minus second order term squared over two things plus a bunch of higher order terms which we're going to ignore. And it's going to turn out, if you calculate this f minus f hat squared second order term divided by 2 sigma squared is going to be this. This turns out to be what sigma squared is right there. This is just we calculated this exactly. We calculated this exactly from very simple premises. All we know is we have a machine. That machine can put out any number of bad widgets, anywhere from 0 to every damn one of them. We've taken some data, data that we had n small n bad ones out of n total big one, total of our sample, and we have deduced everything step by step. There's absolutely no possible mistakes in interpretation. There's no misunderstanding how we're doing all this kind of a thing. We've deduced everything step by step with some twists that we'll get to when we talk more about these things. You can see where this is going. This makes the posterior, the so-called posterior, something like some constant times the exponential of f minus f here times 2 sigma, and this is, I ran out of space, but this is a so-called normal distribution. So here's Bayes, Thomas Bayes' big invention right here. We have to be exceedingly careful, and Jaynes is exceedingly careful in all this. We came up with a normal distribution approximation to the absolute distribution that we calculated of our approximation. So the normal is an approximation to our approximation. It's an approximation to our approximation. The first approximation was assuming the number of possible widgets could go to the fraction of possible widgets could be on the continuum. That's an approximation. It turned out to be a good one. We can make nice calculations with it, and Jaynes will show you in the book. It turns out to be an excellent numerical approximation. It's very good, even for modest size n's. It's either big N or small n. For almost all values of n that are just more than a handful, these turns out to be excellent approximations. But that first thing was an approximation. It was an assumption we made. Let's assume that it's going to infinity on the continuum, the fraction of bad widgets. It was an assumption on our part. We didn't hyperparameterize anything, but once we made that assumption, we were able to deduce what the answer was, which was back a second ago. We were able to deduce what that probability of any particular bad fraction was. And now we're just going to be, for ease, we're going to take a Taylor series approximation of that function. We're only going to do the first couple of terms, which we know we could always do. This is a very nice function. We know we could do Taylor series on this kind of a function up here. And we know if we take the first couple of terms, look at that. How did you guys let me get away with that? We're going to take the first couple of terms here. No, it is negative, isn't it? See, how did you let me get away with that twice? You got to, when you take the derivative. Yes. Okay. And then we came up with this normal approximation right here. This is just that the familiar bell-shaped curve. It'll be centered on some f prime, this f hat rather, which is going to be this value of observed fractions, and it'll be somewhere. It won't be exact because this will be 0 and this will be 1. Here's our bad fractions here, and the normal distribution goes out to infinity, to minus infinity, to plus infinity. So it's always going to be an approximation, but not a bad one. But in the end, all we have to do is stick in. We could draw this picture. We have this value here of f hat, which gives us this value of sigma squared, which is not the sigma squared. The widgets don't have a standard deviation or a variance. The widgets don't have anything like that. The machine doesn't have anything like that. This is just an approximation to an approximation. That's all this is, and that's all any normal is. If we keep that in mind, we're never going to make the mistakes that a lot of people make. This is an approximation to an approximation. And it turned out to be a good one. Useful one. There's nothing wrong with that. But we can never, we're going to make real mistakes if we start talking about true values and all that kind of a stuff. We're really going to be in some deep kimchi. But once we do observe, we've taken a certain number of data and we have this fraction of observed bad ones, we can draw out a normal distribution around that and we'll get a pretty good approximation. And in fact, we can, I guess it's, if you have f hat plus or minus, what is it? I wrote it down before, like 0.68 of the standard deviation. That's the square root of the sigma squared. We get about 50% possibility. And if we take f hat plus or minus 1.65, yes, 1.65 sigma, we get 95% chance. In other words, if we take this particular value and we take plus or minus and the sigma gives us the skinniness or the thickness of this thing. We go on either side of it. We can calculate there's a 50% chance the number of bad fraction of inobservable terms is in this interval. We have a predictive interval. This is, I can't stress this enough. This becomes a predictive interval. This is not an interval of a parameter. This becomes a predictive interval because we are talking about real bad widgets in this case. That's what that F represents. It is not some mysterious parameter of the machine. It is, it represents what we're going to see. So we actually have a predictive distribution on our hand here. So this was kind of a long class and a lot of math, just to show you that we can develop these approximations of approximations. They are very useful to us, but that's all they are. They're approximations to approximations of discrete, finite propositions that we're going to deal with in a predictive way. Now we're going to expand all this and a lot more carefully as we go forward. We've exhausted Jaynes chapter 4. I think we'll go on to, we'll either hit his chapter 5 or we'll start talking about chance, so-called chance and randomness. I think that'll be much more interesting for you. But we had to get this class out of the way. And you have to go back and read Jaynes. It's all free. It's online. You don't have to pay anything to do all this stuff. Larry Brettenhorst put the book up there so you guys can go and read all of this chapter 4 from 4.6 onward. And Jaynes explains every step very clearly. Okay, I went over time and everything, but you get the idea. So more is down here. You can read the lecture notes, all this kind of a thing. And that's it till next time. Thanks much for watching.